We will begin by constructing two great circles on our sphere. I want to make sure that one of them passes through the North and South Pole, which are marked by these little mold marks. I'm going to construct the second circle so that it does not go through the North and South Pole. Once we have our great circles constructed, take your transparency and place it over one hemisphere so that it lines up nicely with the equator. Once you have that in place, we're going to trace the arcs of the circle we just constructed onto the transparency. So you will have one blue arc and one red arc if you're using the same colors I am. Recall that on a sphere, lines intersect 2 times. So we have one intersection here and one intersection at the bottom, and we've discussed that in the past. The mathematician Felix Klein sought to redefine the spherical surface so that lines would only intersect once, just like on the Euclidean plane. To do this, he defined each pair of antipodal points, which are the same as polar opposite points, as the same point. Let's place our sphere so that the side with the transparency is down. Let's call this side that's naked the northern hemisphere, and we're going to mark the North Pole. So by Klein's definition, the North and the South Pole are actually now the same point. So I've marked the North Pole, and I'm going to project this through to the southern hemisphere and mark the South Pole. So again, these are the same points. Flip it over one more time. I'm going to mark where my lines intersect, and I will project that through into the southern hemisphere. Notice that our sphere is collapsing into a single hemisphere. Now we will attempt to pull the transparency off the sphere. Okay, I'm going to move my sphere out of the way. This transparency represents a rough and informal model of the elliptic surface. Note that our lines only intersect one time. As you may suspect, there are some problems with this particular model, notably at the equator, as things get a little bit wonky there. We're going to explore that a little bit and just see what happens. We are going to use the strips of paper. I'm going to move my transparency out of the way. So we have 3 strips of paper. We are going to tape these together so that we have a single long strip of paper, so take a moment to do that. We are going to make a single great circle out of paper. And once you have your single strip of paper, bring your sphere back, and we are going to place this over the equator. And you'll probably have a little bit of extra paper left, and you may want to strip that or clip that off a little bit. I'm going to do that here. So when you're securing this, try not to get tape on the sphere. I did that and it sticks really bad. It does come off with Goo Gone. So I just have a little bit of tape holding it in place. So before we pull this off, I want to mark where my great circles intercept this paper equator. So where my red circle and my blue circle intersect, I'm going to mark that. So with my blue circle, I'm going to make a dot right here. And on the other side, make a dot. And on my red circle, put a dot here. And a dot here. Once you have that in place, we're going to pull the paper equator off. And of course mine just fell apart, that's okay. So that's okay. So remember that on the elliptic surface, antipodal points represent a single point. So we are going to take our two paper clips and attempt to connect our antipodal points. So the blue point to the blue point and the red point to the red point. You might need a little bit of extra tape on your circle. So blue point to blue point. And red point to red point. And this is really hard to do. And you're probably finding the same thing as well. In fact, the only way that this can be done is by introducing a twist into the paper. So now let's introduce the twist. And then it's a lot easier to line these points up and use the paper clips to secure them in place. Yeah, that's lining up nicely there. Now that was challenging just with a single great circle. Consider doing the same thing with the entire hemisphere. You will find that it really cannot be done, at least in our three-dimensional model here. Mathematicians in the past tried to do this and they failed. Moreover, the elliptic surface does not lie in 3 dimensions, but in a 4-dimensional world. And this is where I will stop. For more information on the elliptic surface, check out the resources at the end of our PowerPoint.